my channel, Dr. Sunirban's Chemistry School. Today we are going to discuss about one of very important issues in acid-base chemistry called hard-soft acid-base conceptions. The concept of hard and soft acid-base belongs to the Lewis acid and base conceptions. So Lewis acid basically is nothing but an electron acceptor, so which will have an vacant orbitals, and Lewis base is electron donor, which is supposed to have a filled orbitals. When the Lewis acid and base comes in contact, they will undergo a electron transfer process and they will form a adduct. The basics of Lewis acids and bases belongs to the cations or anionic forms. So Lewis acids are basically metal cations or electron deficits molecules or species, whereas Lewis bases are basically anions or the species which have a available electron pairs for the donations. But question is that whether a Lewis acid, when forms the adduct with Lewis bases, does all the Lewis acids forms adduct with all Lewis bases with similar strength? Let's choose lithium ion as a Lewis acid, and if we allow lithium to select among fluoride and iodide, both are Lewis bases, lithium ion will prefer fluorides over the iodides. That means there is a preference of acid base adduct. Although the nature of adduct is totally depends upon the electron transfer process between acids and bases. But there is no single consistent criteria which can really predict the ease of electron transfer process, and therefore there are different qualitative aspects were given to select or to judge or to compare the basicity or acidity of Lewis acids and bases. And one of the very pioneering work has been done by Pearson, and he stated that hard acids prefers to combine with hard bases. So hard acids likes hard bases, whereas soft acids prefer to bind with soft bases and vice versa. That means the hard acids bind strongly with hard bases, whereas soft acids binds strongly with soft bases. So what the hard and soft does means? Here the hard means small size, either acids or base, that means cations or anions. It should have low polarizability. Therefore, the electrons on the ions are held very firmly or tightly. On contrary, a soft means the size of the ions or species are large, therefore highly polarizable, and diffused electron cloud. But this hardness and softness have a definite criteria, that's true, but there is no finite boundary line between these two, and that's what sometimes some of the ions or acids or bases belongs to the mutual ground, and that's what we sometimes defines a third category or borderline for our preferences. Let's consider how these interactions favored. Let's take a hard acid which is small size and hard base that is also a small size, so they are low polarizable. Therefore, these two acids and bases will interact with each other very strongly through electrostatic interaction. That means the bonds is perfectly ionic, and the interactions is high because charge density is very high, because both of are small size, so volume is less, charge density is high. On contrary, a soft acid and soft bases, which are larger in size and therefore highly polarizable, and a cation can polarize the anion very easily. So polarization means it will polarized, and therefore when they will interact, the orbitals will penetrate very large extent, and that's what a large overlap between the orbitals will leads to a good covalent interactions. So covalency will be maximum when the orbitals overlap very strongly or very largely, and that's what this soft interaction is dominant because of good covalent interaction, and hard combination dominates because of very strong electrostatic interactions. If I take the opposite one, that means hard soft combination, let's consider a hard acid, smaller size, and a soft base, larger size. Since the small cations have a high polarizable category, so it can polarize the softer one, and polarization ultimately leads to a penetration. But in this case, the penetration will not be very deep much because the cation is small, so nucleus can form some repulsive force, and that's what the overlap between the orbitals are not very strong, and that's what the covalency will not be very strong. On other hand, if I take just opposite one, a soft acid and hard base, obviously soft acid cannot polarize the hard base, so polarization is not there, so the interaction is basically electrostatic. But because of larger size, the ion density or charge density is very less, and that's what, although the interaction is electrostatic, but the strength is low, and that's what they are lesser stable than our previous one, where the hard and soft combinations were dominating. Right. If I just take a short or brief looks on what are the ions or molecules or species belongs to this hard and soft category. When we come to the hard acids, as I described, small size and mostly high positive charge ions are considered as a hard, and there should be an absence of low energy empty electronic state, otherwise their electron can be promoted. So for example, protons, alkaline metals, alkaline earth metals, some of the first transition metals with high charge, any ions greater than +4 state, and some of the strong acceptors like carbon dioxide, cyanides, sulfur trioxide, and so on, and any type of HX molecules which can undergo hydrogen bonding, they are considered to be hard. On contrary, softs are larger size, obviously the ions should be at 0 or low positive charges and presence of easily excitable valence electron that can leads to the some extent fill upping the empty orbitals, so their electron hungerness will reduced, and that's what they are soft. So the transition elements with low charged or lower transition elements like 4D and 5D, some of the components which have very less electron hungerness, and the metal at its zero oxidation state, even the pi acceptors like quinone, tetra, cyanoethylene, these molecules are also considered to be soft acid. However, there are some of the ions or molecules which belongs to both of these category, or their properties are in between something, and that's what I said, that there is an existence of borderline. Among that, some of the transition elements in +2 oxidation state like ferrous, cobalt, nickel, copper, zinc, some of the transition elements of lower group with high little bit moderate charge, +3 charge or something. So and also boron with trialkylide components, these are soft. little soft acids, and that's what called borderline. But obviously, although these are hard or these are soft, but still there is also something hardness is varies between the cations and anions. Okay. Now, if I comes to the base, a similar explanations or definition can be given. For example, hard base means high electronegativity, low polarizability, presence of localized field orbital. It should not be delocalized, and absence of any low lying empty orbitals, otherwise the electron will be promoted to its own orbital. So these are hard, like ammonia, primary amines, oxide donors or any kind of oxo donors, carbonate, nitrates, phosphates, sulfate, even the fluoride and chloride as a halides. On contrary, the soft bases are low electronegativity, high polarizability, the electrons are partially filled or delocalized, and obviously the presence of low lying empty orbital will reduce the donation capacity. So these are the soft bases. For example, hydrides, larger halides, pseudo halides, sulfur donor atoms, some of the pi donors like ethylene, benzene, carbon monoxide, phosphorus donor, and so on. So these are soft bases. And there are some intermediates like phenylamine or any kind of aromatic amine, pyridines. In these cases, the lone pairs of nitrogens are delocalized over the ring, and that's what they get reduced. So any kind of resonating molecules where the electrons are resonated or delocalized, those are some extent softer, and that's what we fall in borderline cases. Now, this conception of hard and soft acid bases definitely have some advantages to explain several phenomena, and largely any kind of acid base reaction now can be understood through this hard soft terminology, and the basic guidelines for these explanations of natural phenomena are based on a very straightforward conception that hard and soft combination always dominates over hard soft combination. That means hard combination favored, soft combination favored, but hard soft combination is not a favorable combination between the acids and bases. Let's consider complexation. If I consider ligands like fluoride, amine, water, because basically these are hard bases. So hard bases always prefers hard acids, and we have observed that these kind of ligands always form very stable complexes with ferric, cobaltic or titanium plus 4 state. These are quite hard. On the other hand, the phosphines or thioethers or sulfides, they prefer very stable complexes with the palladium, platinum, mercury, these kind of soft acids. So these soft bases makes a stable complexes with soft acids. So therefore hard and soft combination dominates. So hard soft combination can explain the complexation behavior. If I come to the some exchange reactions, for example, a components of this kind, adduct like BF3 and hydride when form a adduct, this BF3H minus, here BF3 we know the hard acid, hydride is a soft. So this combination is hard soft. Here BH3 which is soft acid, fluoride is a hard. So this is also soft and hard combinations. When they will allow to react, they easily exchange their ions. That means BF3 combines with fluoride, BH3 combines with hydride. Now this combination is hard and this soft, and the equilibrium shifted much towards the right side. That means our hard and soft combination dominates or favored over hard soft combination. Similarly, alkaline earth or alkaline metals halides, if I consider lithium iodide, which is soft and hard soft combination. Cesium fluoride, since cesium is softer metal than lithium, so we can consider soft hard combination. So these combinations are according to the hard soft combination not favorable, and whenever we mix these, they will form a precipitation of lithium fluoride and cesium iodide. That means in this case hard and soft combination favored over this ion. So easily it moves towards the right side. So this ion exchange process also governed or also can be explained through hard soft combinations. If I briefly look on the solubility and we consider the silver halides as our example. So silver fluoride, silver chloride, silver bromide, iodide. When we critically looked on the solubility of these halides, we found that the solubility gradually decreased from silver fluoride to chloride, bromide and iodide. Iodide is the least soluble. That means silver iodide resist against solvation, right? That means it is not going to solution, so it is resisting. Why it is resisting? Because silver is soft, iodide is also soft. So soft combination is favored over soft and hard, because silver is soft, fluoride is hard. Therefore this soft hard combination is weaker one and it goes to the solution. So it cannot resist against the solution. But silver iodide, because of a strong interaction, it resists against the solution. Therefore solubility also can be explained. If I take the opposite one, a lithium cation and different halides, where as expected lithium fluoride being as a strong or hard combination, it resists the solvation, whereas lithium bromide cannot. Although there is an exception in the lithium iodide which is supposed to be highly soluble, but because iodide is a very bigger anion which have the very less solvation energy, and that's what its solubility is some extent lower. Although the solubility of lithium iodide at least 100 times higher than the lithium fluoride. So that means lithium fluoride is dominating. Now if I come to the preference of donor atoms, for example, if I take a ambidentate ligand like thiocyanide, which usually found to be form a complex either through sulfur end or through nitrogen end. And as our sequential, we know that sulfur being as a large polarizable end, it is softer end, whereas nitrogen being a small one is a hard one. When you critically looked on some of the metal ions like cobaltic, nickel, cobaltus, so on, these are basically some extent harder one. Whenever they form complex with thiocyanide, they prefer the nitrogen end. That means hard combination is favored. Whereas soft metals like palladium, platinum, mercury, they always combines with thiocyanide through sulfur end. That means soft is dominating, right? Therefore this complexation of an ambidentate ligands also goes according to the hard soft combinations. That means hard combination or soft combination always dominating. If I goes to the find out the mineral abundance, that means in our earth crust there are a lot of different type of minerals set there of different metal ions, starting from alkaline earth metal, transition metal, post transition metal and so on. Whenever we found that the hard acids like alkaline earth metal or some other transition metals, so these are mostly found in the earth crust as a combination of hard acids like chloride, sulfate, carbonate or oxides. That means most of the abundant minerals of these hard acids are of the countercation are hard bases. So the preference of hard acids with the hard base is favored. On contrary, when we are looking at the soft metals, we always found that, or mostly we have found that they preferred sulfide as their counter anion in the minerals. That means here soft combination is favored. So although we have observed that several reactions, abundance, solubility and different phenomena can be easily explained on the basis of hard soft combinations, where hard and soft combination dominates over the hard soft combination. But always we have to be very precautious, or we have to take cautions whenever we explain any other phenomena with this hard soft combination. We have to keep in mind that what are the other energetic terms are associated with the reactions. For example, if I looked on acid base as I mentioned already, they are either hard or soft, but at the same time they can be strong or weak. So the strong weakness and hard and softness, they are comparable and they are always competitive. So we have to keep in mind. For example, a sulfite, a soft but strong base, whereas fluoride is hard but weak base, and proton is a strong as well as hard acid. So this case hard combination must be favored if I consider hard soft acid base. But in contrary, sulfite replace the fluoride and form the HSO3 minus. That means here, rather than hard combination, the strength of the ions or strength of the base plays a role. So stronger base replace the weaker base. So here the strength is dominating. So we have to be careful when we deals or explain a reaction, that whether other phenomena are also plays a role or not. Similarly, a strong base replace the relatively weaker base for this ion. Although this is soft, this is also soft, but still stronger base replace the weaker base. Similarly, whenever we are talking about the solubility, we have to be very cautious, because a solubility means that the two things are plays role. One, the component stability, that means the compound which have the cations and anion, how strong their bond is. And the second one is the solvation energy. That means whenever this compound goes to the solution, the corresponding ion is solvated. So solvation energy released when the cations solvated. So larger the solvation, more energy is released. Now if you carefully look at the strength, or we can say the hardness of these acids, although all are hard, but still their hardness is varies from smaller to the bigger one, and hardness is in this trend. So magnesium is the most hardest one and barium is the most weakest one. Therefore when we compare the solubility of carbonate is the hard one, right? So magnesium carbonate, calcium carbonate, strontium carbonate and barium carbonate. So our expectation is that magnesium carbonate, since magnesium is most hardest one, so this compound is most preferable, most stable, and this is the weaker. So since most stable one, so therefore this should be the least soluble and this will be highly soluble. But oops, exactly the opposite trend is observed. So why? Although magnesium carbonate is, according to the hard soft, is favored, but still when it goes to the solution, because magnesium being a smaller ion, due to high positive charge density, solvation energy tremendous, whereas barium, the bigger one, solvation energy less. So the solvation energy, due to the lesser solvation energy, barium carbonate cannot be breaked into the solution, but because of high solvation energy or exothermic reaction, it ultimately goes to the solution. That means in this case solvation energy dominates over hard combinations, right? Okay, so I hope I have make you some of the doubts regarding this hard soft combinations. Try to clear it. So if you really likes my presentation, please subscribe my channel Dr. Shunirban's Chemistry School, and please don't try to forget the bell icon. In that case you will get the updates about all the uploads. And if you still have any kind of queries or any kind of suggestion, don't hesitate to email me. My email address is sunirban.chemistry@gmail.com. So thank you very much.